All right, welcome everyone. In this lesson, we're going to see how to calculate the derivative of a composite function. And we're going to be learning another one of our big derivative rules, which we call chain rule. So first of all, though, let's start by just reviewing what a composite function is. And this is going to be an important idea, so it's worth kind of taking our time to just review over this idea of composition. So let's start with the definition. A function h is the composition of two functions f and u if it can be written in this form. H of x is equal to f with u of x inside. And so sometimes we also use this notation to denote a composition. So we read this as f composed with u. It's a little open circle there. And then f composed with u of x. So it's going to be a function. This is generally, though, how we work with these functions. And so when we read this, we tend to think of it as there being an inner function and an outer function. And so when we look at this, f here, we tend to think of as the outer function. And that's because it's on the outside. And then we think of u as the inner function. And that makes sense because u of x is inside the parentheses here. It's in this big set of parentheses for function f. So when we work with a composition, what's really going on is we tend to think of this process. Oh, you can think of it almost as like an assembly line. That's how these functions kind of work. So we start with our input x. And the way the composition works is we kind of start where we see x in our little formula here, and we work our way out. So as we take this raw material x, we put it through the assembly line. The first thing that happens to it is it goes through this function u. So it goes into our inner function u. And then inner function u kind of changes our input, and it gives us something out. It gives us u of x out. And then we take u of x, and we plug that into function f. So u of x goes into function f, and that's our outer function. And then what does function f do? Well, it gives us ultimately an output. And so the whole output of this process is we have f of u of x. So we've taken u of x and we've plugged it into our function f. So there's this kind of assembly line process here with composition. We take our input x, goes into our inner function u. That spits something out, which we call u of x. We take that number, plug it into our outer function, and then that returns ultimately the output of this composite function. And so we can kind of view a composition of two functions. We can view this as sort of one function of its own. So we could view this as function h. So we start with function x. It goes into this machine function h, which ultimately gives us out f of u of x. So this is kind of how to picture composite functions. It's almost like we're on an assembly line, and it's just working our way through. We start with our inner function, and we work our way through. All right, so let's do a little bit of examples with these composite functions. And in the first one here, we're given two functions, f of x, which is secant x, and u of x, which is x cubed, and we're going to calculate two different compositions. So in the first one here, we're going to calculate f of u of x. And when we look at this, f is the outer function, u is the inner function, the way this is written. All right, so let's see how this is going to look. So we want to calculate f of u of x. And let's start by replacing this u of x with what we know u of x actually is. It's x cubed. So essentially what we want to do is we have f of x cubed, and what we want to do is we want to go to our function f, and wherever we see an x, just replace that with an x cubed. So what is our function f? Well, it's secant. It's the secant function. And instead of an x here, we're going to replace that with an x cubed. So our outer function was f of x equal to secant x. And what we did is we looked at each of these x's, and essentially we replaced them with our inner function, which was x cubed. And that's what we did right here. So this is secant of x cubed is this composite function. And you can kind of see secant is the outer function and x cubed is inside the parentheses, so it's the inner function. Now, we're going to try another one. This time we're going to reverse the order. So instead of doing u first and then f second, now we're going to reverse the order. F is going to be the inner function, so we're going to do that first. And then u is going to be the outer function, so that's going to happen last. So what does this composition look like? So we're going to write down our composition that we want to do, u with f of x plugged in. Let's change what f of x is. It's the secant function, so this will be u of secant x. And so what we want to do is we want to go up to our u function, and wherever we see an x here, we want to replace it with a secant x. So let's write this out. We have u of x is equal to x cubed. And so wherever we see an x here, we want to replace that with secant x. All right, so what do we get? We're going to change this x to a secant x. We're going to get secant x cubed. And we'll put the secant x all inside a pair of parentheses here. So it'll be secant x cubed. Now, we can rewrite this. So sometimes we rewrite these powers of trig functions. We put the actual exponent on the actual trig name. So we would normally write this as secant cubed like this. But it's fine to leave it like this. Secant of x all cubed. All right, so that's a little practice there actually calculating the composition. Now that's not the only game we're going to play. So we're going to be working with these composite functions quite a bit when it comes to derivatives, and then later on when we get to integration too, we'll be talking about these composite functions. So this is a really important idea, and a lot of the really interesting functions that we're going to be looking at in the course are in some way a composite function. So it's going to be really helpful to work with these. So this is actually calculating the composition. Now in the next example, what we're going to do is we're given 4 different functions, and we want to kind of break these functions apart and identify what the kind of the composite pieces are. So we want to write each of these functions as a composition or a composite of 2 simpler functions. So we want to identify the inner function and the outer function. That's really the game we're going to play here. Identify the inner function and outer functions. And really there's not always one right way to do this. But one kind of strategy that we're going to use is wherever you see parentheses, look inside the parentheses, and usually that's going to be your inner function. So let's look at this first one. H of x is equal to x raised to the power 4 plus 9x plus 3, all raised to the power 8. And so the inner function is everything inside the parentheses. It's what happens first. The outer function is what happens at the very end. So if we were going to evaluate this, we'd plug x in. First thing we would do is raise to the 4th. Then we do plus 9x, then we do plus 3. And then once we have that whole result, what we would do is we would raise that whole thing to the power 8. So raised to the power 8 is the very last thing we're going to do. That's going to be our outer function. Let's see where we want to write this. So f of x is going to be x raised to the power 8. And our inner function is going to be everything inside the parentheses. So it's going to be that x to the 4th plus 9x plus 3. And we'll call this u of x. Now sometimes, just so that we don't have all these different x's floating around, sometimes we give the outer function a different variable. So we're using x's in our main function here that we're interested in. We're trying to break it apart. Let's use x's for our inner function, and then we sometimes use a different variable for our outer function. And a lot of times we just make this a u. So another way to represent this is with, we might say f of u is equal to u raised to the power 8. So sometimes it's helpful to picture this composition where we kind of introduce a different variable here. And so our inner function is usually inside parentheses. So if we see parentheses in our function, look inside of them. That's usually going to be our inner function. And for our outer function, this is everything else. This is normally what happens last. So think about just, if you were actually going to plug a number into this and type it into your calculator, what would be the last thing you would do? Well, you would raise everything to the power 8. That would be the last thing you do. So that's going to be our outer function. Now let's look for this next one. H of x is equal to sine of x to the 4th plus 9x plus 3. We want to identify the inner function. We want to identify the outer function. And so when we're looking at this, I see a set of parentheses, and I see the same polynomial inside the sine function. So if I were going to evaluate a number in this thing, plug a number into this thing, and then evaluate on my calculator, the way I would go through it is I would take the number, raise it to the 4, then plus 9 times my number, then plus 3, and I'd have a result. And then I would take that result and plug it into the sine function. So the inner function is going to be u of x, and it's going to be that same polynomial that we had in that first example. And our outer function here is going to be our sine function. And we could be using f of x if we wanted to. And so way to kind of picture what the outer function is just kind of cover up everything you're saying is going to be the inner function. So I'm saying that this polynomial here is going to be my inner function. So what am I left with? I'm left with cover that inner piece up, and everything else then is going to be my outer function. So sine of x, or sine, and just decide on a variable to use. So we could either write this as sine of x, or really to emphasize the composition, we might say f of u is equal to sine of u. All right. So just getting a little practice, kind of having a function and being able to break it apart into two simpler pieces from a composition. Now in the next one, e raised to the x to the fourth plus 9x plus 3, we don't see parentheses here. And so for exponential functions, what's inside the exponent is going to be our inner function. So again, think of how you would actually type this into a calculator. If I were plugging in, say, the number 2, I would first raise 2 to the power 4, then I'd add 9 times 2, then I would add 3, and I'd have a result, and then I would take that result and plug it into the exponential function. So the very last thing I'm doing is this exponential function, and the very first thing I'm doing is plugging the number into the polynomial. So imagine, to figure out the outer function, you could just imagine kind of covering up what you're saying the inner function is going to be. And then your outer function is just everything else. So in this case, it's e raised to the power. It's our exponential function. So I could use variable x if I wanted to. So it'd be e to the x. Or to really emphasize that we're going to do a composition, I might change this to variable u and say f of u is equal to e raised to the power u. All right. And then last one, just to get a little practice here, h of x is equal to the natural log of x to the fourth plus 9x plus 3. Kind of a similar situation to what we saw with the sine function. So that polynomial is inside the parentheses. Kind of what happens first. And then that log function is on the outside. So it's the thing we do last. So that's going to be our outer function. So f of x is going to be, if we want to write it as a function of x, which is fine, natural log x, or to really emphasize the composition, we sometimes might use variable u. So we would say f of u is equal to the natural log of u. So this is going to be an important kind of skill that we're going to use throughout the course. Given a complicated function, being able to recognize that it's a composition of two functions, and then being able to kind of break that function apart into an inner function and an outer function. All right. And you could play the game just like we did in the first example, where you could work backwards. And if you know those two pieces, then you could actually calculate their composition and you should get back to where you started. So as a for instance, let's try this. Let's try the first one here. Let's actually look at f of u of x for this first one. So let's replace u of x with our polynomial, x to the fourth plus 9x plus 3. And then I'm going to take this x to the fourth plus 9x plus 3, and wherever I see an x right here, I'm just going to replace that x with parentheses x to the fourth plus 9x plus 3. So I'm just going to change this x to that polynomial. And you see we get right back to where we started. That was our original function. So these two functions that we decided on, you can always check your work here. Calculate the composition, and you should get back to where you started. All right. In the next video, we're actually going to introduce the chain rule. So how do we differentiate functions like this? So far, all of the rules that we've learned do not tell us how to handle functions like this. They only tell us we've looked at how to handle if we just have addition or subtraction, constant multiplication, product rule, so if we have the product of two x terms, or the quotient, if we have the quotient rule, if we have the quotient of two functions. Now, composition is something else entirely. So it's not quite any of those operations, our usual operations. Composition of two functions is something different. And so we have a special rule, which we're going to see, that will enable us to differentiate all these different functions. So we'll see you then. Bye.